Let's discuss an innovative concept of desktop farming. This setup can be used to grow plants in temperature-controlled environment. Crops grown in traditional outdoor farming depend on supportive weather and suffer from undesirable climate changes. Producing food indoors reduces or eliminates conventional plowing, planting, and harvesting by farm machineries, protecting soil and reducing emission. Traditional farming is often invasive to native flora and fauna because of its required such as a large area of arable land. In comparison, this system overcomes this because of its limited space usage. In previous videos, we have demonstrated measurements of soil moisture, temperature, and also constructed a thermoelectric cooler. The links for the same is added down in the description. In this project, we will be combining the three for a desktop farming application, that is, growing plants in a controlled and automated environment on a table. Here is the flow diagram of desktop farming. The temperature sensor and the moisture sensors are used to take inputs of soil's temperature and moisture data of each plant. Thermoelectric cooler is used to maintain the temperature inside the chamber. Let's look at the block diagram. The block diagram consists of PT1000, which will be the temperature sensor to be used in the system, that is connected to a bridge where a differential voltage is generated. The generated differential voltage is converted into a single-ended voltage using an instrumentation amplifier. These single-ended outputs are given to a signal reconfiguration board. FC28, which is the moisture sensor being used in the system, is connected to a voltage divider where sensor voltage is generated. The generated voltage is provided to a voltage follower using unity gain amplifier. The output of the amplifier is accepted as input by an analog to digital converter, which provides a digitized output to a processor, where temperature and percentage moisture is calculated. The thermoelectric cooler is connected to the driver board, which will control the temperature. This is the whole stack setup, where PS represents the power supply board, BM represents the bridge module, IA represents the instrumental amplifier, SRC represents the signal reconfiguration board, IB represents the input board, UGB represents the unit gain board, and ESP represents the ESP32 grower module, and MD represents the motor driver board. The new board that we are using to configure the signals from the temperature sensor, which are alternative, are being routed as consecutive using signal reconfiguration board. So the signals A, C, E, G, I, K, H and O are routed to A, B, C, D, E, F, G, H, which are consecutive in nature. Our test setup consists of an acrylic chamber filled with soil. Temperature and moisture sensors are placed in different regions. Thermoelectric cooler is fixed on one wall of the acrylic chamber with heat sinks attached on either sides. The required temperature is set using serial monitor, and it can be seen that the temperature inside the chamber is adjusted to the set temperature. Thus, we can see that the temperature sensor array, moisture sensor array, and thermoelectric cooler can be constructed using e-Lagori boards in just about 30 minutes.
Visit www.e-lagori.com for more details.